Good afternoon to all of you. Welcome to yet another session of Cisco CCNA. Remember, we are doing CCNA-1, Introduction to Networks. We have already covered 5 chapters, and now we are going to do Data Link Layer, Chapter 6, Module 6. If you look at the OSI model, my dear students, you will realize that right at the bottom, the first layer is your physical layer. Above that is your data link layer, layer 2, okay? So we are going to study a little bit more about this layer. You will study, I believe you have already done so, in detail about the data link layer and the physical layer in your lecture session. First of all, we'll ask the question, why do we need a data link layer? What is its purpose? Okay. What are the topologies that we have on LAN, on WAN, and so on? And what is the data link frame look? What does it look like? Okay. So we'll be looking at some of these. Actually, the information given here is not as extensive as what you have learned in your lecture, but it's still informative. So why do we need the data link layer, the second layer of the OSI model? Okay. First of all, it's responsible for communications between end device network interface card. Okay. When you think about your network interface card, always remember you are talking about your data link layer. Okay. Your MAC addresses all is controlled in by your data link layer. Okay. If you want to communicate with the upper protocols, okay, it goes through data link layer, and then from upper protocols to bottom protocol to physical layer, again it goes through data link layer. Okay. So what happens actually when it's coming down, okay, when your data is coming down to the data link layer, okay, in the network layer, it is in the form of packets. You see, layer 3 packets. So this layer 3 packet has to be encapsulated into data link frame, okay, and vice versa. The layer 2 frame will be decapsulated back into packets, okay, packets into segments, segments into data, so that your application can read it, okay. Primarily in your data link layer, we are interested in the NIC's MAC address, okay. This is the hardware hard-coded hexadecimal address, okay, that is coded inside your machine, any device, any device that is joining the network, okay. Can be even an IoT device, as long as you have got a NIC, a network interface card, okay, you have got a MAC address, okay. So data link layer and protocols on data link layer take care of that, okay. Another important aspect of this data link layer is error detection and rejecting corrupt frames. This is very important, okay. If there is rejection, then you can send it all over again. And you know, your data link layer within the local area network, when you send data from one device to another device, it only can recognize faster through the MAC, because the MAC is unique. But the moment when you leave the network, okay, the moment when you leave the network, as we studied last week, then you need layer 3 IP addresses, okay? And layer 3 IP addresses are IP version 4 and IP version 6. This morning session, I touched on that. We talked about the numbering systems. We talked about the binary numbering system. That's what the machines understand. And we talked about the hexadecimal numbering system, something which is used for MAC addresses, as well as for your IP version 6. Okay, IP version 4 uses decimal addresses so that we understand. But those decimal numbers, the machine understands only binary. So those decimal numbers have to be converted back into machine. Okay, so don't forget to go through the lecture of the morning so that you're abreast with what you have to do next week. If you look at your data link layer, it consists of two main sublayers. It has got the LLC and the MAC. The logical link control, okay, it is responsible, you see, as it says over here, it communicates between the networking software at the network layer and upper layers and the device hardware at the physical layer, the bottom layer. Your MAC sublayer is the second layer, and this is responsible for encapsulation and decapsulation. Okay, actually, just encapsulation. It takes the packet, encapsulates it into a frame, and sends it down to the physical layer. Okay. Now, at each hop, if you're going from one network to another network, the moment you see the word hop, that means you're traversing a router. Remember that. Okay. So at each hop, a router performs 4 basic data link layer functions. Okay. The first one, it accepts a frame from the network medium. Second, if it accepts the frame, it has to send it up. Okay, we are talking about this now. You see, it's going this way. Okay, so the data link layer accepts the frame. Now it has to decapsulate the frame and give it to network layer as a packet. Or if it's coming from the top, the network layer will give it a packet, and that will be encapsulated into a frame by your data link layer. Okay. So this is something you have studied in your lecture in detail. Now here we're just touching the surface of it. Okay. There are some standards which is maintained by some engineering organizations with respect to data link layer protocols, and these are IEEE, ITU, ISO, and ANSI. Okay. Now let's go into some topologies that we use. Remember, data link layer is mainly dealing with the physical rather than the logical. Okay, the network layer deals with the logical. So when you look at topologies, there are two kinds: physical topology. Every time you do a lab, we give you a physical topology. We tell you this is how it's going to look. This is your devices. This is your switch. If there is a router, we'll put that also in the topology, and then you start building it. Okay, by using a real equipment, or you can simulate first on packet tracer to make sure that everything is working. Okay. Logical topology is mainly taking into consideration the IP addresses, okay, and the interfaces. That's why for logical topology, you see, they will give you a table with all the IP addresses. It may be version 4 or version 6, depends. So when you think about, did I miss anything here? No. When you think about WAN topologies, wide area network topologies, you got point to point where you have got one device connected to another device. Straightforward, right? Okay, following the IEEE RFC guidelines. You have got the hub and spoke, where it's just like a star topology, a switch at the center, and everything else connected to that. And a mesh topology, okay, where you have got every end system connected to every other end system. Okay, you don't need to do that, but that is also another option. So let's look at our point-to-point topology in a WAN situation. Okay, the nodes may not share the media with other hosts because all frames on the media can only travel to or from the two nodes. So the point-to-point topology, in this case, as you can see, two nodes of a router are connected to each other. So they are using a DTE wire, okay, a serial DTE wire, something that we are going to use in CCNA 2 and 3, definitely not in 1, okay? And this allows your point-to-point WAN protocols to be implemented when you connect two nodes, okay? Talking about nodes, let's do a small experiment by using our Cisco packet tracer. Just give me a second. So what I'm going to do is, let's do a quick experiment. You see, when I connect two switches, okay, I'm going to connect them by using, let's connect to fast Ethernet 1 to fast Ethernet 1, okay. There you can see they are amber, okay. That means there is a connectivity. They can connect to each other. And after some time, you can see that this amber becomes green. Okay, so no issue. I mean, I haven't even given IP address to the VLAN, but you see, it's already amber. So we know that this amber is going to become green, simulating exactly what you have. See, there it is. It's become green. Okay, simulating exactly what you have in the lab. In the lab, also, when you connect two switches, first it becomes amber. When you see the light amber, that means, okay, everything is fine. The switches, the end nodes are working, the straight through cable I'm using is working, everything is okay. Now let's do the same experiment. Now this time with we do it with a router. Okay, I take a 4331 router. Okay, and I'm going to do the same thing. I'm going to use the same. Remember, it doesn't matter if you use crossover or straight through, because they have got that inbuilt negotiation. Okay, and it will, no matter which one you use, it will automatically ensure that communication still happens. Now, again, I use over here for this router, I use, let's say, gigabit Ethernet 00 connected to gigabit Ethernet 00. The moment I do that, you see, you get a red symbol. A red symbol meaning there is no connectivity. You see, here I didn't have to do anything. I just connected there. Connection established. But here you see, nothing. Why do you think there's no connectivity? What is lacking over here? Can anyone tell me? Between these two routers. Point-to-point connectivity. You see, this is the DTE clock connection. You see, you have to give a clock rate. But here I'm just using a straight through cable. Anyone? What should I do so that these become green? Anyone? Remember, a router is used to connect one network to another network. Very simple. What I have to do is I have to give a IP address, okay? And doesn't even have to be, belonging to the same network address. Let's just experiment this, okay? We go to the command line interface. See, simulating exactly your router. Would you like to enter the initial configuration? No. Okay. Enable conf t. Okay, now I'm going to give an IP address to my interface. My interface was, if you remember, my interface was, what was my interface? G00, right? Interface G000. Okay, there we go. And then I give IP address 192.168.1.1. Okay. And subnet mask 255.255.255.0. Okay. No shut. So it's immediately implemented. Okay. Done. Exit. Exit. Okay. Show IP interface brief. There you can see my gigabit Ethernet 00 connection is 192.168.1.1. Okay. And the interface is running. But there is no connection yet, you see? But it's up and running. Now, what I do is, let's go to the second one here. We open this. We go to the command line interface. Okay. Again, the same thing. Would you like to enter the initial configuration? No. Okay. We are dealing with a router here, my dear students, not a switch. Okay. But the iOS commands are mostly the same. Enable, configure, terminal, giving an IP address for the interface G000. There we go. IP address 192.168.1.2 in order to put it in the same network as the other router. But what I'm going to do is I'm going to put it in another network. You see, I'm going to say 2.1. The moment I put 2 over there, that means it's going to be on another network. It doesn't match the previous router. Okay, but still, we'll see whether there is a network connectivity. Okay, so 255.255.255.0. Okay, just like before, no shut, implement it. Okay, and then show IP interface brief. There we go, 192.168.2.1. Remember, the previous one was 1.1. This is 2.1. Now, the $1 million question is, has that red light become green light? Let's see. There, can you see? Okay. You can see it has become green light. But the question, another question is, can I ping from here to here? Remember, they are not on the same network. I mean, they can be on the same network, but I have not given the same address. Okay. So you can see you're physically, since you have given an IP address, you can have a connection. But over here, if you want to ping, let's just ping. Okay. I'm going to ping my first router, ping 192.168.1.1. That was the IP address. And you can see that I don't get any ICMP return. Okay. ICMP is your pings. Okay. Yeah, 0%. Why? Because they are two separate networks. In order for them to ping each other, I have to put them in the same network. Okay, so let's do that. Let's go back here again. Conf T interface G0, 0, 0. I have already given IP address. What I'm going to do is give a new IP address. So the old one is going to be overwritten. Okay, so IP address 192.168.1.2. Okay, remember the other router was .1.1. Now I'm putting in the same network, .2. Okay, 255.255.255.0. They should be on the same subnet mask. Okay, no shut. Exit. Show IP interface brief just to make sure. Yes. Now I'm going to ping my other router. Ping 192.168.1.1. It should be 100% success. 80%, never mind. Now it will be 100%. Okay. So this is something that, experiment that how routers behave and how switches behave. Okay. Very soon you will be doing lab sessions on routers, but not yet. Now let's go back to the lesson. These are some of the topologies that we have. We have got a physical topology in terms of star, which is usually a switch over here and all the computers connected to that switch. There used to be an old device known as hub, okay? But nobody uses that anymore. It's very difficult to find it, even if you look for it, okay? A switch is a much more faster device, okay? We also have extended star topology. If you connect a switch with another switch to both these switches will be connected to an aggregate switch. That's how a modern network looks, okay? Now, besides that, we have got legacy applications, old ones, which was the bus topology. I remember my first network, when I went to my first network lab, they were using a Unix network operating system, okay? And this was back in India. And they had they had a bus topology, okay? And I remember back in those days, the lab that we had, I think we had only 30 computers. And only a few of them had color monitor. And everybody used to fight for that color monitor. All the other monitors were, monochrome, or black and white. So our server was a Unix-based server in those days, okay? We also had another legacy, which was the ring topology. A token ring will send the data, and whichever PC's ID is there, it will go in there, okay? Now, when you have a communication, the communication can be half duplex or full duplex. Obviously, full duplex is what we need, okay? Both devices can communicate simultaneously at the same time. For example, our Ethernet switches, that's why they're very fast, okay? Half duplex will only allow one device to send or receive at a time, okay? The old technology where we had got hubs was, half duplex. So sometimes when both of them send at the same time, they will collide and the data will be lost. So they have to send again. So that was an issue, okay? So that's why we don't use hubs anymore. They're old technology. But half duplex communication still goes on, okay? In certain communication that we have, which is CSMA-CD, okay? Carrier sends multiple access with collision detection. We also have CSMA-CA. You have studied this in your lecture as well, my dear students. CA is just like this, but collision avoidance. Our wireless LANs, they use this. Okay. Basically, CSMA-CD, okay, will ensure that if there is a collision another random timer will be given to whichever device, and that random number again they will send. But again, if there is a collision, again the timer will be reset. Okay. Besides this, we also have old systems like control access used in Token Ring and ArcNet. But now let's go to CSMA CD, used by certain legacy Ethernet local area networks. Okay. And it has got a collision detection process. So every time it detects a collision, okay, it will wait for a random period of time and then retransmit that data again. Now, this technology obviously works in a half duplex mode. It's not the best, but it is improved in terms of CSMA CA, collision avoidance. Again, this also unfortunately works in half duplex mode. But what it does is it uses a collision avoidance process. Okay. So how does it do that? It ensures that the time needed for the transmission, okay, that time is shared with all the other devices. So all the other devices, what they do is they will not share until that device has finished. Okay. So other devices on the shared medium receive the time duration, and they know they have to wait until that device is finished. So that's why they call it collision avoidance. Okay. Now, let's look at the frame, data link frame. Okay. Remember, a data link frame consists of three parts: header, data, and trailer. What is inside the data of a frame? Very simple. Inside the frame, we have got an encapsulated packet. Okay. So let's have a look at how it looks. So here we have got a frame header consisting of the start, that's the beginning of the frame, the address, that is your MAC address, okay. The type over here encapsulates the layer 3. The control identifies the flow control, and here is your actual packet, encapsulated packet, okay. Besides that, in the trailer, you have got error detection and frame stop. If there is error, it will communicate with the sender, and the sender will send the frame again, okay, to ensure that nothing is lost. So layer 2 addresses, data link layer 2 addresses are dealing with our NIC addresses, MAC addresses. So every time we'll have a destination MAC address and the source MAC address. Okay. This will continue until it leaves the network. That means goes through the gateway, the router. Inside the router, there is a table with all the MAC addresses. Okay. So that's how it identifies the devices on the network. Yes. Who's that? Yes, GN. Because it has to carry other information: source, destination, source data, source address, destination address, and so on. Okay, amongst other things. And if something gets lost, you have to again send it back. Okay. In your lecture, actually, how it does that, how that data, the window, there is something called sliding window. How that data sliding window is increased, what algorithm they use. You will study those details in your lecture. It's actually very interesting. Okay. So when you're talking about your MAC address, your NIC, it's used only for local delivery of a frame on the link. The moment you go outside the network means outside the router, then we are talking about your layer 3, source IP address and destination IP address. Now, in your data link frame, okay, so in this layer, some of the logical topology and physical media determine the data link protocol that we use. They are Ethernet. They are the wireless 802.11 standard. It is the point-to-point. It is the HDLC, high-level data link control, and is frame relay. And each protocol has got certain purpose and certain function to do. Okay? Perhaps some of these we will be studying more about them in other chapters. This brings us to the end of the session. Anyone has any question before we move on to the next item? Okay. Today, what you have to do is the same task as what the students did in the morning. You have to experiment and work with a new software called a packet sniffer software, which is an industry standard. Everybody uses it, which is called Wireshark. Okay. So I have a link on Moodle on how to install Wireshark. So your task is to install Wireshark. After you have installed Wireshark, you open it. Okay, there you see, it opens Wireshark. It shows my network. Okay, so look at my Wi-Fi network. You can see my local area connections. Okay, is pretty much non-existent. And then my Wi-Fi, you can see. Okay, it shows me my address, which is IP version 6 address over there, and even also IP version 4 address. Okay, so if I go and open a website, if you look here, let's say I go to CNN website. When I open CNN, look, can you see the spike? Every activity I do, you see, you can see the spike. Okay, so I go to my Wi-Fi, and you can see the detail of the communications that I have. Can you see? Now, your task is to open one connection. First of all, download and install Wireshark. And then next, what you do is you go here, and we are only interested in the ping data. So I type ICMP. Okay, here. I type only ICMP. So once I type ICMP, you see, it will only look for ICMP communication. Now what I do is, I'm going to ping. Okay, so I go to command prompt. Okay. Sorry. There's a big microphone in front of me, so access to keyboard typing is difficult. So what I do is I ping Google. Okay. Now, the moment I ping Google, sorry, spelling. The moment I ping Google, okay, there is supposed to be some activities over here. Now it's delayed, you can see. What I do is I ping something else because I've already pinged that before. Now I'm not getting a response. Let's say I ping another server, perhaps my ISP, 192.168.0.1. Okay. The moment I ping my ISP, you can see the activity. Okay. You know, at the ISP end, they will immediately, they have a software that this client, this user, this customer is using a packet sniffer software. Okay, they immediately will know, and they will study me and try to know, to try to see what's going on. Okay, so it's okay. It's just that we are not doing anything malicious. We're just looking at the data. You see, it tells you every details. Okay, now what you can do is you can stop this, and you can even save it. Before you start a new one, you can actually save this information. Okay, to get the details of it, you can go over here and to see more details. So this is your task for today. What you are going to do is you're going to actually download your Wireshark and show me some network activity whereby you do a ping. First, you select ICMP over here, so we concentrate only on ping. And once you ping, there should be some activity. Most probably, your ISP, internet service providers, and their IP address also will be the same thing, 192.168, because you are essentially connected to a router. Okay, so probably theirs also is 192.168.0.1. Okay, but first ping Google and see whether it works. And first of all, download the software, and then from there, we can show me one by one. Okay, that brings us to the end of this. So I stop the recording.